Very good morning also from my side and from IIASA in Vienna. What I'm going to present on is a study on a paper or like a presentation on a paper that we recently published and that is coming out of a group project called Provide, where we looked from a wide and interdisciplinary background on the question of climate overshoot and what to say about it. I am right now experiencing a technical issue, which manifests itself in my PowerPoint not moving forward. So I will just start. Oh, here we go. Just basically quickly saying what this presentation is not about. It's not about the question whether or not we will exceed 1.5 or how do we determine this. And if anything, I think some of the discussions that we're having in that space are also a bit overconfident from my humble perspective. So that's probably also something that we can touch up on the discussion a little bit. And I'm also not going to say that the question of pursuing something like a long-term temperature decline is a bad idea or something that we should not aim for or should consider undesirable. Probably quite to the contrary. So maybe after this quick disclaimer of what I'm not going to talk about much, I still want to set the scene, of course, in terms of where we are when we discuss questions of climate overshoot, because it commonly refers to the question of exceeding the 1.5 degree limit of the Paris Agreement, and then aiming to draw temperatures back down again below that level in the very long run. This is very topical right now because we are very probable to have 2024 as the first year above 1.5 degrees. We all know that a single year does not mean that the long-term limit of the Paris Agreement is being breached, but obviously it means we are becoming dangerously close, and on the trajectory that we are currently on in terms of our current pledges and policy emissions, we will certainly exceed 1.5. There are some studies in review that try to map that out, so we're probably going to see the crossing time of 1.5 if we don't bend the emission curve very drastically within the period of the next 20 years. And that's something that we need to consider, but we also need to be mindful that the fact that basically our ability to determine the human attributable component of warming from a long-term trend, as a long-term trend from a time series that is also subject to natural variability comes with some uncertainty. So the IIASA working group 1 has assessed basically a half a degree likely range in terms of determining the human attributable warming over the decadal time period, which basically means we're probably going to only be able to say in hindsight with certainty that we have exceeded 1.5. And it also means it's going to be probably rather difficult to, with confidence, detect overshoot situations that link to just a couple of tenths of a degree. So, for example, being very confident that we are in a low overshoot situation of 0.1 degree might actually be challenging from the observational record alone. So we need to keep that in mind also in terms of how we look at these questions and frame them. And then uncertainties obviously amplify going forward. So this is a sketch figure from our recent study, trying to map out this space a little bit, and in particular being mindful of mapping out the temperature space in this case, where we would end up in different temperature trajectories for even the same emission scenario. So we may do the best we can. We try to get to net zero, for example, at mid-century. We felt we would have a limited overshoot, maybe limiting warming to around 1.6 or 1.7 peak. But then it turns out the climate system is not friendly to us. Turns out the climate response is higher than we think, and we end up in a much higher scenario or a much higher warming outcome. Similarly, we might find that some technologies don't work out the way we think, that our basically, transformational pathway perspective ends up different. And ultimately, we probably rather look into a cone of different future outcomes, out of which basically, and I want to focus on this a little bit, we would classify those that basically get to net zero CO2 and then hopefully peak temperatures and achieve long-term temperature decline as peak and decline pathways, out of which an overshoot pathway is just basically one possible outcome, because an overshoot in this case would refer to getting back to a specific temperature level at a specific point in time or over a specific time frame, whereas one could argue basically that might be a bit over-specific if we consider physical climate uncertainties all the way in our framing of these scenarios. All right, in our study and also in the project that I've been leading, we've been trying to look into the implications of overshoot all the way down the impact chain. So from the emission pathways to the global temperature outcome, regional climate impacts, and then the adaptation and loss and damage consequences. And I want to start at the bottom there. And Veronia, you already highlighted this is an area of your interest. Very interested to hear your comments on that. But if you think about adaptation and needs for adaptation and adaptation planning, then one of the first things that we want to think about when we discuss overshoot are timescales. So this is basically an illustration of a rather low and a higher peak warming overshoot scenario. And in both cases, you see basically you have an overshoot period that is several decades long, if not even half a century potentially, or more. And the question is, how does this compare actually to adaptation timescales? And these are now basic different adaptation timescales for planning strategies, or also lifetimes of different options, but also questions of how you basically evaluate these adaptation options in a cost-benefit analysis, for example, assuming different discount rates. And what you basically obviously can defer or deter the use of, already from that graph, is that the question of a long-term temperature reversal over decades may be of limited relevance for adaptation and only apply to very specific cases, for example, for long-term infrastructure design, because ultimately adaptation planning horizons are decadal, 20 to 30 years at max. And if this is your adaptation planning horizon, then obviously peak warming is a lot more important than the long-term climate outcome. So in this way, you can already say, well, basically the framing a pathway as a, for example, 1.5 overshoot pathway might be even a bit misleading for adaptation planners, because it should rather be, for example, a 1.6 or 1.7 peak warming. I just got a message that someone doesn't see my slides. Are other people seeing my slides?
Yes, we are.
Thank you. Okay, excellent. So maybe you can help them out there. But this also doesn't even consider the fact of whether or not regional climate impacts are actually reversible. So we also looked into this a little bit. That's another study by Peter Fleiderer and Jana Simon and myself. And this is basically looking into the regional annual mean temperature questions in the CMIP ensemble around peak warming and then after. And then the question, if you actually went to peak warming and back down again, would the regional trend actually reverse or not on the ensemble of different CMIP models? To be very, very brief on this, and there's a lot more to say about this. If it's green, it means it's reversible or be classified as reversible. If it's blue or red, it means it's either an under or an overcompensation of the signal. And what you do see is that there's not so much model agreement, so a wide range of different outcomes, but also in particular, the notice that even something that you would assume being rather reversible, like annual mean temperature, doesn't really reverse very, very well. There's a lot more to say about this also in terms of effects that happen, basically long-term climate stabilization effects and dynamical changes of the climate system. But in the interest of time, I keep this very brief, but there's a lot more also in our study that we did on this particular question. I just want to highlight that obviously after even at 0 CO2, we have ongoing adjustments in the climate system over the timescales of centuries. That's another paper from our study that just kind of looked specifically at different overshoot pathways up to 3 degrees and back down again to 1.5, and the evolution of the Atlantic meridional overturning circulation in the GFD-LESM model. And what you do see there is the AMOC exhibits a recovery in all of those scenarios, but in the scenario of a temperature overshoot, it even exhibits something like an AMOC overshoot centuries down the road. So what the takeaway message here is basically overshoot is coming with a long-term legacy in the climate system. And basically, there's not really a going back to where we left off, even if we were to reverse global temperatures. Then there are obviously irreversible impacts, and there we would leave a clear legacy of overshoot. This is now showing basically the temperature equivalent of permafrost and peat-like climate feedbacks, so permafrost and peatland melt, as well as in blue and median sea level rise, global sea level rise in purple. And 100 years of overshoot would, in the median estimate for moderate overshoot scenarios, commit about 40 centimeters of sea level rise in 2300. If we crank this up to the 95th quantile and we're crossing some irreversible thresholds of the climate system, this could be up to 1.2 meters. We see similar results for glaciers and other cryosphere impacts, but also, for example, and this is a rather open question, what about biodiversity risks or species extinction? are they also going to be showing in a similar long-term irreversible damage behavior. Another study that we looked at is the question of irreversible thresholds, specifically looking at the Amazon, the Greenland, Western Arctic ice sheet, and the overturning in terms of triggering irreversible dynamics of those systems. On the current pathway, we would see about a 50-50 chance of tipping by 2300, even if we brought temperatures back down to 1.5 again. But we also in particular see a strong increase of every additional 0.1 degree of temperature above 1.5, and then even more so for a peak temperature above 2 degrees in terms of the risk of crossing at least or triggering at least one of those irreversible systems of the climate system. Small caveat here, neither the tipping points nor the response times are particularly well constrained. So this is obviously exploratory research in some way, but I think it indicates already that also there's a irreversible risk or legacy risk from overshoot that we need to take into account when exploring that question. Moving now one level up to the question of emission pathways and global temperature, because also there we have a tendency to draw graphs like this. So this is an emission graph that actually limits peak warming or like warming around 1.5 in black, and in red is the central temperature curve from the FAIR model. And the way these pathways are framed in the mitigation literature is also in the AR6 working group 3. We have limited and high overshoot pathways. They refer to by about 0.1 degree of overshoot or 0.1 to 0.3. This gives a very precise numbers and kind of communicates the feeling that we are very much in control of the thermostat in that way. But if we now looked at the broad range of different FAIR outcomes, you would see that for the same emission pathway, we could have physically plausible warming outcomes that are a lot higher than 1.5 and even show long-term warming if the zero emissions commitment wasn't actually zero, but actually positive. So if we take all these things into account and actually look into the physical climate questions more generally, then we might need negative emissions to even just stabilize warming after we achieved net zero CO2. And if you wanted to go back to where we thought we would go on the median outcome, we would probably also need a lot of carbon dioxide removal or cooling after stabilization. And we did that kind of looking into the question and asking ourselves, well, if you not just looked at the scenario uncertainty, but the geophysical uncertainty, how much carbon dioxide removal would you need? And then the number I want to highlight is a little bit kind of the 75th quantile, which is marked by this red bar and this bar plot at the top. And that's a 1 in 4 outcome over a pathway where we think we wouldn't have any overshoot. And in this pathway, we would need about 400 gigatons to get to where we thought we would go in 2100, which is comparable and very well in the range of the scenario uncertainty of AR6 emission pathways, which means we might actually need a lot of carbon dioxide removal to hedge against high warming outcomes. And this has broad implications also for the question of pathway design. So instead of saying we can be fully confident that we can reverse warming and it's all going to be fine and we have 0.1 degree of an overshoot and this is how we should frame the question, we may rather want to think about this in the context of limiting long-term, near-term and long-term climate risks. And then being able to also address those risks, for example, by building up something like a preventive capacity of carbon dioxide removal that we could use to reverse temperatures in terms of high warming, in terms of a positive outcome or a central outcome of warming response to emissions. But if we are unlucky and we are looking into a high warming, high risk world, this would hedge against such high warming outcomes. Having that said, I want to conclude quickly by just commenting on why I want to reverse warming in the first place, because obviously being able to reverse long-term warming might be critical to actually minimize climate risk and our climate legacy over centuries to come. This is again showing something like I've shown before on the permafrost and peatland loss, but also additional sea level rise. And you'd see that basically achieving net zero greenhouse gases as by the Paris Agreement and thereby in the best estimate the long-term temperature decline would reduce the long-term sea level rise commitment by about 40 centimeters and in the 95th quantile even above about 1.5 meters. So you'll be able to still basically reduce some of the key pressures that are going to unfold for centuries from climate change right now on human societies and the global coastline. Similarly, similar results for again also the question of triggering tipping points of the climate system. Achieving net zero greenhouse gases might be one of our best shots it's still limiting long-term risks, even in the case of overshoot. Staying up there, staying well above 1.5 definitely is a very risky strategy in terms of triggering some irreversible responses. So you want to aim for an overshoot and you want to hedge for high warming outcomes. And I want to conclude, I know this was a bit of a tour de force through a range of different aspects, but it's a truly interdisciplinary topic. I want to conclude with some key takeaways from our project and this particular study as well, that overshooting 1.5 is risky and comes with irreversible consequences. The best strategy to limit climate risks is still reducing emissions and sprinting basically to net zero as fast as possible. We all know this, but I think it is important to re-emphasize that point also in the light of the insights on overshoot. But even though overshoot might be not a desirable scenario, needing to aim for long-term warming reversal is still an important part of a strategy that hedges against high-risk outcomes and long-term climate risks. And I stop there. Thank you.
Super, thank you, Carl. That was really, really interesting. So whilst we wait for people either to put questions in the chat or pop their hands up, I'll kick off with a question. So if you were talking to the climate adaptation community at one of their big convening conferences, such as Adaptation Futures, what would be your key messages for them? And whilst you're thinking about your answer, for those of you that are unfamiliar with Adaptation Futures, it's the flagship event of the United Nations World Adaptation Science Programme, and it happens normally about every 2 years. The next one's in New Zealand in October next year. So, Carl, what would be your key messages to the climate adaptation community?
Thanks, Bernie. I think a key message would be to engage in this overshoot discourse to start with, because I think right now it's a discourse that lacks basically the voices of this community. Because I think it's important to illustrate or further substantiate what I tried to imply, that maybe, for adaptation, peak warming is what matters. And an overshoot is not another way to get to the same outcome, but ultimately the needs and also costs for adaptation will be determined by peak warming. I think that's, for the policy debate, would be an important part, that engagement. The other part to it, and I think that's something that we studied also in the project, and I can invite you to explore that on the Provide project website. I'm happy to share that in the chat as well. It's that obviously overshooting a global limit or global threshold is one way of framing the overshoot question. Another way would be to actually look at adaptation limits in the local context, for example, for ecosystem-based adaptation, and the risks of exceeding those and those thresholds on the local level, and what it does mean for basically your adaptation portfolio that's available to you under overshoot scenarios, and how you basically incorporate these risks of also high warming or high climate risk outcomes in the local context when considering adaptation limits. There are some methodological similarities as well. That would be my 2 points that I would try to stress towards an adaptation community. I don't know if you agree, but that would be my start.
Thank you. No, I think they're very interesting, and I think you should submit an abstract for Adaptation Futures. Whilst we were doing that, actually, there's quite a few questions that have come through. I can see Helene's got her hand up, but I think Jarmo came in first on the chat. So Jarmo's asked, what drives the AMOC overshoot?
So there's a lot more to show there, and in our paper we also compared 2 different models where we had 2,500 simulations, and they show very different behavior. Ultimately, in these models, the AMOC is largely like the thermal component of the AMOC is dominating, which is also why you don't see an AMOC shutdown or anything like that, but you do see basically a response. And what you see is a time-lag response of that system that is currently weakened under warming by basically Arctic amplification. And then if you reverse global temperatures, you would basically reverse that trend too. So you would almost kind of overfuel the AMOC, and you would see basically then an overshoot in the response in the same way you've seen basically an undershoot in the near term. So it's a strongly nonlinear dynamic. We have in the paper also looked at the NORI-SM model that also had like 2,500 simulations available. It showed an even stronger response of the AMOC in terms of decline, and not quite the same in terms of overshoot, but a similar, let's say, strongly nonlinear response in the scenario of global temperature decline.
Hopefully, Jarmo, that answers your first question.
Yep, perfect.
Great. What we'll do is we'll go to Helene for her question, and then Carl, could I ask you to answer the other 2 questions in the chat, and we'll move on to the next speaker. So Helene.
Yeah, thanks, Carl. That was super interesting. It's great to be talking about the overshoots, because as we know in CMIP 7, that will be one of the overshoot experiments will be part of the AR7 fast track. So it'll be great to see results from a wide range of system models. But my question was about the sea level commitment. So although you showed that it would be reduced, is there not still a chance that by, peak warming might still push, say, the West Antarctic ice sheet to collapse, and thereby we may still see these very high-end sea level numbers that we previously talked about?
Yeah, very much so, which is why I also showed the 95th quantile, where you do see that this is a lot higher. I mean, ultimately, the question of how ice sheets would respond in an overshoot scenario, I think, is one that is currently subject to deep uncertainty, because we do not know the timescales and the periods of overshoot under which these systems would actually be responsive. But ultimately, yes, if you lost it altogether, like one of the components, for example, then this commitment would play out irrespectively of your future warming trajectory. But as we also showed in the other study, with a purely stochastic approach to what we currently understand about the systems, it still appears beneficial to draw temperatures down in the long run, because it might actually help to still stabilize those systems if we are unsure whether or not they are already in an irreversible state. So I think it's an open question. For other systems, obviously, ocean heat uptake and glacier loss, you would see some reversibility over the timescales of a couple of centuries. So there you would see the effect for sure. And for the ice sheet response, I think it strongly depends also where these tipping points lie and how fast they are being triggered. So it's an open research question. We have a sea level rise model that does take it into account, but we are far away from being able to say this is the projection and this is what we know about the response of the systems in an overshoot trajectory. That's, I think, is an important research question for all of us to tackle.
Yeah, absolutely. No, thank you so much. And yeah, a great advert for what we need to do moving forward.
Thank you.